Hi everyone. Really apologize for stand between you and the beautiful launch, but it's live. And in today's talk, I'm gonna revisit benchmarking graph query. Sorry. Oh, right.
Oh,
Yeah. So today I'm gonna revisit benchmarking graph analytics, and this is a work collaborated by Shanghai Jiao University and Alibaba Damo Academy. And for me, this is Longbin Lai, and I'm from the graph scope team at Alibaba Damo Academy. And this talk was originally presented by Professor Xu Meining from Shanghai Jiao University, but unfortunately couldn't make it to the meeting, so I'll present this talk on behalf of him. So speaking of benchmarking graph analytics, we certainly have to mention the LDBC graph analytics benchmark. I think we really appreciate this work, as otherwise a lot of progresses on graph processing will not be possible, and certainly we're not going to have today's graph analytics challenge in TUC meeting. I have no idea when the results are going to be launched tomorrow. Sorry.
so there's a TUC meeting tomorrow.
Oh yeah, that's great. So yeah, speaking of this graph analytics benchmark, actually it's the first industry-grade benchmarking platform for graph analytics, which have the following 5 requirements. And today we'll focus on revisiting requirement number 2. The benchmark must include a diverse representative benchmark elements, including algorithms and data sets. And requirement number 3, it must have a diverse representative process. And requirement number 5, it must follow a modern software engineering design. And first of all, why we want to revisit the benchmark? Our first argument is the algorithm selection procedure by LDBC. It end up with the selected algorithm. They are representative but not diverse. So here's the 5 algorithms selected by LDBC. They are breadth search, page ranking, weakly connected component, community detection by label propagation, local clustering coefficient, single source shortest path. And these 5 algorithms, except local clustering coefficient, have been pointed out to have very similar computing patterns, which we call ISVP here, standing for interactive, single-phased, and value propagation-based. And people have been constantly used these 5 algorithms to test their systems for whatever reasons. If we simply count the appearance in the public in the publications, and certainly they will be selected out, right? So this is why we argue that they are representative, but they are not diverse. Right. So what's our proposal in this algorithm selection procedure specifically? So the first step is we categorize the existing graph algorithms in 7 classes that has been intensively studied in academic, and this will end up with these 7 classes. And as we can see, the selected algorithms by LDBC, which is enclosed in the blue box, they only cover like 4 out of 7 categories. And then our algorithm selection procedure, it is multi-dimensional. First of all, we want the algorithm to be evenly spread across the 7 categories we have defined in the previous page. And secondly, we do counting their appearance in academic publications, but not arbitrarily, but per each category. So in this way, they will be spread across these categories, right? And thirdly, in addition to simply counting their academic their appearance in academic publications, we also count how much have been searched in the academic search engines, including DBLP, Google Scholar, and Web of Science. And this really helps us identify important algorithms like Longbin, which is less frequently mentioned in academic publications, but it's very frequently searched in these engines. All right. And finally, we refer to a typical sequential implementation of this algorithm and refer to its time complexity as the textbook complexity of this algorithm. And then we really want the selected algorithms to have a large variation in terms of this textbook complexity. As we can see, these algorithms, they have linear, super linear, even to the square yeah. And with this procedure, it really helped us identify these 8 core algorithms. We present it as a 8 core algorithm, but certainly more algorithms will be evaluated and added to the benchmark procedure in the future. And our second argument is about datasets. We say the selected datasets by LDBC are narrow in terms of characteristics and sizes. And regarding characteristics, LDBC use both real graph and generated graph. And for real graph, it includes social network and knowledge graph. And for generated, it borrow data sets from SMB and Graph 500. But we found that these data sets, no matter real or generated, they either follow like the typical small world graph model, which require that every pair of vertices must be within a very small distance, typically 6, or they follow a well-known parallel graph model, where the degree sequence of the graph follow a parallel distribution. However, graph in real life practice, they are more diverse. For example, the road or route network, they are typically sparse, very sparse, right? And like for product customer graphs, they are bipartite. And we can name many more graphs with the other characteristics other than these 2. And in terms of sizes, and we recognize that the largest real-life data set, like Twitter MBI, included by LDBC benchmark, they have only around 2 billion edges, which is way too small to benchmark large-scale graph systems, right? And we do recognize that in this graph analytic challenge, and much larger data sets have been included. So this really motivated us to add more diverse and large-scale graphs to the data set. How do we do that? So we propose to generate large data with real-life characteristics. And luckily, at Alibaba, we do have a diverse business as well, with massive graph data. For example, here, the Gauder, it's a map application. It do host a very huge road network at China. And Taobao is a famous e-commerce platform in China. It hosts a like trillion scale customer product network. And for AliGraph, it actually produces massive network traffic structure. And we cannot directly publish this data to for obvious reasons. But what we can do is to profile the characteristics of these graphs. And based on the profiling characteristic, we can develop a massive data generator. I think this is, this afternoon we will have the fine bench. I think they use a similar method. And then what we're going to revisit is the benchmark process. Although LDBC benchmark, they include a comprehensive metrics covering like the perspective of performance, scalability, and robustness. And what we really argue is these benchmark metrics, they are quite platform oriented without concerning the user experiences at all. What do I mean by user experience? So we want to add it to the benchmark, not only the platform oriented metrics, but user oriented metrics. For user oriented metrics, we simply cover like these 2. Expressiveness concerning whether user can implement certain algorithms in the platform, and productivity, how easy can user implement certain algorithm. And this is what the user and what they really need. If you have a system with superior performance, but user find it really hard or even not possible to implement certain, but whatever to be, the value will be not delivered, right? And finally, we revisit the software design. LDBC graph analytics called it modern, but what we argue is it's modern but not golden. It's based on several issues that we encounter while using the benchmark. The first thing is software dependency issues, because obviously the benchmark rely on Java. And for example, if a Java version conflicts, it's really hard to tweak into make it really work. The second thing is repeated generation of some data. As you can see, because there's no place to host this, although we have a standard generate procedural, but it really is kind of time consuming. If you generate this, especially very large scale data, like the scale 3K or something, it takes days. And finally, to benchmark large scale system, we have to deploy the benchmark toolset with the system. And it is really hard to do that in its current state. So our proposal is for the benchmark toolset to go cloud native. We might want to use the Docker image to resolve software dependency issue that I mentioned. And we may open the public cloud services to archive some, generate data for you to convenient usage directly to benchmark without repeatedly generating them. And we might leverage things like Kubernetes to help us easily deploy the tool sets with a large scale system. But wait, there's one more thing. We're talking about more algorithms and more larger data sets and more metrics to evaluate. This complicate the benchmark so that they will prevent users from actually using them, right? So our proposal is a thing called benchmark hierarchies. We have currently considered 3 levels in the hierarchy. So in the most internal level is what we call the core level. It includes the 8 core algorithms we've selected in the previous slides, and the others remain the same as the LDBC graph analytics. Okay, and we think that this core layer is very suitable for like computation and challenge. And then the medium level is what we call the massive layer. It includes the 8 core algorithms, but we add more massive data sets and with the cloud-based services into it, but with a perf metrics data same as graph analytics. And this will be suitable for people to prove of concept their system, specifically for large scale. And the most peripheral layer is what we call the production layer. It will include more algorithms to the benchmark that we are considering like 20+ algorithms. And with all the massive data set, cloud-based services, and user-oriented performance metrics. And we think that this layer is suitable for new systems to showcase its capabilities to the market. I'm here to accept any question. Thank you very much for this.
Thank you. Very interesting work. So you say 8 core algorithms and others remain as Graphalytics. Do you mean the data sets?
Yeah.
So data sets remain the same as Graphalytics?
Yeah.
Okay, excellent. Yuan?
Thank you.
Nice work. I really appreciate that you
Thank you.
really look at the algorithm selection, but I do have a question with the algorithm, right? So you look at academic research papers and look at academic search engines. Seems like you're just looking for a signal from the academic side.
Yeah.
I'm not sure that really represent what the industry really wants, right?
Oh, yeah.
So how do you address that?
Okay, this is really nice question. But we actually count the number of the appearance while you search for that keyword in, for example, Google Scholar, and that would include whatever paper that mentioned both from the academic and the industry. I think you probably could introduce the other search, for example, directly search this in Google. But using a Google Scholar, for example, they would make it much less noisy as far as we're concerned. Thank you.
You can just repeat the question so I'll be quick. How do you measure expressivity and productivity?
All right, good question. So for expressiveness, well, what our initial try is to implement the algorithm by ourselves, by seasoned engineer as best as we can. if they cannot do, for example, like 1 week of exploration, and we will consider it's very hard, or that's how we measure expressiveness. And for productivity, we simply measure its the line of logical codes.
Oh, that's
Like-
bad.
Oh, yeah.
No,
I-
that's terrible.
Yeah, I got it. Yeah, I got that. You know,
Okay.
this is not necessarily a gold standard, but this is one of the standard, and we will definitely consider refining the procedure as best as we can. Thank you.